These are very close, and the point is that these are some of the closest galaxies by which telescopes that we have, moderate-sized telescopes that astronomers use, including amateur astronomers, can all resolve stars, and certainly the Milky Way, and using moderate-sized telescopes on mountains in Hawaii and such like, you can resolve stars in M31. You can see the individual stars in Andromeda, in Triangulum, and in lots of little dwarf galaxies. Because the local group is a very diverse place. This is the Andromeda galaxy, a very famous picture. I may sometimes slip and call it M31, but it's the same thing. Here you can see a beautiful image, sort of a quintessential disk galaxy. It also has, though you'll notice, two very bright small galaxies right next to it. Okay, one is called NGC 205, the other is called M32. These are small dwarf galaxies, but you'll see they're right next to this bigger galaxy, and that's something we will come back to again. As well as the Andromeda galaxy, you also have the Triangulum galaxy. This is another object which you can see certainly with binoculars, perhaps even naked eye, but I believe it's binoculars. This, sometimes I might accidentally call it M33. This is a galaxy that's about 1/10 of the size of Andromeda. And Andromeda is about the same size as the Milky Way galaxy. So it's a big galaxy, but it's not on the same scale as Andromeda. It's not on the same scale as the Milky Way. It is, however, significantly bigger than a galaxy like this. Here you see now we have an elliptical galaxy. This elliptical galaxy, however, is a dwarf galaxy. Okay, it's actually much smaller. It's maybe roughly 100 times as small as the Triangulum galaxy, or 1,000 times smaller than, say, the Milky Way or the Andromeda galaxy. So this is, what we call a dwarf. It's much smaller, but you can see it's still just a perfect elliptical galaxy. And then you also have a galaxy like this, NGC 6822, not a very great name, I must admit. This is more irregular looking. There's more things going on. It's not just a ball of stars. There's also interesting things going on because this is actually forming stars. These are just an example of some of the galaxies that are out there. This image, or this graph, really, of where all these galaxies are, is not the most attractive, if we're being honest. And it's also actually a little bit out of date. So what I'm going to do is I'm going to show you a fly-through, or some of a fly-through, of the local group. This is, of course, not an actual fly-through of the local group, or you would have read about it in the news. Rather, this is a simulation of basically all of the positions of the galaxies and where they all are with respect to each other. We come in from the top, and then we're going to do a figure of 8 around the Milky Way and M31 and Andromeda. And then we're going to go out. Now, my colleague who made this, John Dubinsky, is absolutely fantastic in movies, but I think he's made so many of them that he feels he needs to do something else when he makes them. So we were talking about it, and so this actually has a soundtrack. Now you might think, well, galaxies, Rachmaninoff, what's going on? This is actually Kanye West and Katy Perry. So, something to show that we're young, we're hip, and all of that. In fact, actually, I might be too used to the festival because I've just remembered that the Kanye West part is not family friendly. So instead, I'll switch it back on in a moment. Here you instead, though, see the Milky Way, you can see the Andromeda, but you can see immediately all of the dwarf galaxies around them. Okay, these galaxies cluster around this nice galaxy. Just to show you what it's like with the soundtrack. Oops. Oh, I need to go back, I'm afraid. Yeah, so actually that's quite good because you get to see M31 again. The galaxies, the dwarfs, effectively cluster around the Milky Way and M31, but you notice they're spread throughout. Most of them close to Milky Way, most of them close to M31. Some of them incredibly close. You'll see there's one or two actually look as if they're inside the main body of the Milky Way galaxy, and that's because they are. Okay, the two bright ones at the bottom are the LMC and SMC. Okay, the Large Magellanic Cloud and the Small Magellanic Cloud, and these are two very bright dwarf galaxies. This part is about to be a big flip. This is... It's very cool, as you can tell. So that's I like music when it does the spin. However, here you can see the Andromeda galaxy. Again, those two galaxies that you saw in the image, NGC 205, M32. The spiral structure we basically just put in by hand. This is an amazing, if you like, laboratory. And in fact, I like to view, that's just spin, is just for fun. I like to view this as kind of a laboratory, okay, because this is the laboratory in which we can actually dissect, if you like, a galaxy, dissect it into its component stars, okay, to try to figure out what's going on, how is it put together. Now, many of the galaxies here, there's about 73 galaxies in total in our surroundings in what we call the local group. Most of those, except for the ones I highlighted, Andromeda, Milky Way, M33, Triangulum, are dwarf galaxies. One of the incredible things about dwarf galaxies, for which there's far more interest than there should be, is that they're very dark. And I mean that in a very specific sense. What you're actually looking at here is a picture of the Ursa Minor dwarf galaxy. So it's not one of the faintest galaxies we know, but it's a faint galaxy. You can't actually even see it. It's not that's just a bright star at the center. You might be able to see a slight increase in the number of stars, number of blue points smattered around in the central regions. But you can't really even see this galaxy very well. Okay, it is there, and when you sort of count stars, you can see there's a galaxy there, and deeper images show it up a little bit better. But the point is, this galaxy is nothing to look at, really. Okay? It's insignificant. So why would you be interested in it? Well, there's two reasons, and basically this forms the basis of most of what I want to get across to you tonight. The first is, as well as seeing that stars are there, we can actually measure how they move. Okay, so this was actually done in the 1980s. A person called Mark Aronson. He basically observed 3 of these stars. Okay, and what he did was he took a spectrum of their light. So he splits their light up into a rainbow. Okay? Now, because that light is emitted from a star, which has in it chemical elements, that's where a lot of the chemical, well, in fact, all of the chemical elements which we know come from the stars. So because of that, there are signatures imprinted in that spectrum, which tell you about the types of things that are in that star. Okay? Now, when you hear an ambulance go past, and I was out obviously at Case today, and so with the medical center there, you hear lots of ambulances go by, and you hear a change in pitch as they go by, because as they're approaching towards you and then going away from you, there's a change in the as they disappear off. That is called the Doppler effect. Okay, and it's that same effect that allows us to actually measure how stars move. Okay, because that change in pitch is a result of the fact that the thing that is giving off the sound, as it's coming towards you, all of the waves, the sound waves, are being bunched up. Okay, because it's racing towards you and the sound waves sort of, it's catching up with the sound waves almost, and so therefore it's being compressed, and so there's a slightly different pitch to the signature. When it's going away from you, it's stretching out the sound waves. So again, there's a different change in the pitch. So too is the same thing with light. Okay, some of these stars are moving towards us, some might be moving away from us. It doesn't matter. As a star is moving towards or away from us, there's a Doppler effect that you can see in the light when you take a spectrum. So for example, do you see I'm going to walk away from the microphone here. This feature here, you'll notice you can identify the same feature in all of those three spectra, but they're at slightly different positions. Okay, that means those stars are actually at slightly different velocities. Okay, that means you can actually measure how the stars are moving. Why do things move? They move because of gravity. They move because they're falling towards something or they're being pulled towards something. Okay, so by measuring how these stars are moving, we're actually measuring how much mass there is that's causing it to move in the first place. In other words, we're weighing up this dwarf galaxy. Okay, that's the basic principle. We can look at the light from the stars, we can see how they're moving, and because they're moving as a result of gravity, and gravity is caused by things having mass, we can actually figure out how much mass is in galaxies, and in this case, in dwarf galaxies. Mark Aronson did this in 1983, and it's been redone many, many times for many galaxies all over the place, but particularly for these dwarf galaxies. And this is a major industry today, because what we find is that there's far, far, far too much mass in these galaxies for what we can actually see. Okay? We can count the number of stars. We know how many stars should be there. So we know roughly how massive this galaxy should be on account of all of the things that we can see in it. But that's nowhere near enough mass. And there must be an awful lot more mass in the galaxy for the stars to be moving like they are. This was published, yes, so did I get the year right? Yes, 1983. This is my only sort of major ugly-looking plot here. But what it emphasizes is this. Things at the very top are very massive. Things at the very bottom are not as massive, okay? And basically, things over on the left are very faint. So the faintest dwarf galaxies we know about lie over on the left as you're looking at it. But you notice those really, really faint things are very high up on this scale. Because what that scale is, it's not a measure really of mass. It's a measure of how much extra mass do we need over and above the mass that we can actually see to account for how the stars are moving in them. And so you see for some of them, galaxies called names like M32 there, the amount of mass that we imply is in there compared to what actually should be there is only 2 or 3. In other words, this only has maybe 2 or 3 times the amount of mass that we would expect from just looking at it. Okay, so maybe no major problems there. Right up at the other end, though, you're seeing that these things have 100 times more, 1,000 times more, nearly 10,000 times more stuff in them than there should be on account of everything we can see. This is not the only evidence for this substance. This is just one of the lines of evidence that after exploring this for a very, very long time, the conclusion seems to be that these things must have an awful lot of dark matter. What is that? If you ever find out, it's a guaranteed Nobel Prize. Who knows? The point is, for everything to work like we think we understand things, and this is just, remember, one line of evidence, these things actually are some of the most dark matter-dominated things. That is, they have more dark matter, more mysterious substance that we don't know what it is, compared to things that we actually understand, stars, than any other objects in the universe. That makes them incredibly interesting things to study, to try to understand what on earth is going on with this thing which we call dark matter. However, for all of that, for all of the fact that these things are far more massive than they should be, they're still not all that massive. That means they are actually susceptible to being bullied, if you like. That is to say, bigger things have a much stronger effect on them. Why? Because small things are perturbed or are affected more by what's going on in the surroundings. A collaborator of mine, long before he was a collaborator, long before I was in astronomy, was looking towards the center of our galaxy, the Milky Way. And just to sort of orientate you, there is the galactic center is there, and the disk is there, and the pattern is due to lots of dust and such like in the way. He was looking towards the galactic center, trying to understand how stars move around and what their chemistry is like towards the center of the galaxy and what we call the galactic bulge. He did that, and he found something that he couldn't explain. And like all good, he was a student at the time, so like all good students, when you have something you're stuck on, you go to your supervisor, and you say, hey, Mr. Supervisor, Mrs. Supervisor, I'm a bit stuck here. What's going on? And his supervisor dutifully told him, oh, you must be wrong. And go away. I think was the following sentence. So he did. And he watched it some more. And he thought, actually, I think I'm right here. So he went back and said, no, you're still wrong. Go away. And this carried on for some time. And the bottom line of it was, eventually, he managed to convince quite a few people that he wasn't wrong, that there was something going on in the center of the galaxy that couldn't be explained, until actually they found what the explanation was. And that is, towards the center of the galaxy, there is another galaxy inside of our own galaxy. That is this blob that's just shown as contours because it's very faint, and so it doesn't stand out well in a picture if it wasn't highlighted. It turns out this is actually a bit behind the center of our galaxy, but it's in the same line of sight. This is a galaxy inside our own galaxy. This is kind of a bit weird, particularly at the time when this was never really thought of before. We call it Sagittarius because if you look for it, you have to look towards the constellation of Sagittarius to actually see it. You won't be able to see it. This person, after he's been out celebrating a few times, he claims he can see it in the night sky, but we think that's probably due to other reasons.